direct current meters. The D'Arsonval meter movement. D'Arsonval meter movement or permanent magnet moving coil, PMMC, meter movement. The moving coil mechanism is generally set in a jewel and pivot suspension system to reduce friction. Another method of suspension is the top band suspension system, which provides a more sensitive, but more expensive, meter movement. As a matter of comparison, a typical full-scale current for a jewel and pivot suspension system is 50 μA, whereas a full-scale current of 2 amperes for a top band system is entirely practical. Horseshoe-shaped permanent magnet with soft iron pole pieces attached to it. Between the north-south pole pieces is a cylindrical-shaped soft iron core about which a coil of fine wire is wound. This fine wire is wound on a very light metal frame and mounted in a jewel setting so that it can rotate freely. A pointer attached to the moving coil deflects upscale as the moving coil rotates. Current from a circuit in which measurements are being made with a meter passes through the windings of the moving coil. Current through the coil causes it to behave as an electromagnet with its own north and south poles. The poles of the electromagnet interact with the poles of the permanent magnet, causing the coil to rotate. The pointer deflects upscale whenever current flows in the proper direction in the coil. For this reason, all DC meter movements show polarity markings. It should be emphasized that the D'Arsonval meter movement is a current responding device. Regardless of the units, volts, ohms, etc., for which the scale is calibrated, the moving coil responds to the amount of current through its windings. D'Arsonval meter movement used in a DC ammeter. Since the windings of the moving coil are a very fine wire, the basic D'Arsonval meter movement has only limited usefulness without modification. One desirable modification is to increase the range of current that can be measured with the basic meter movement. This is done by placing a low resistance in parallel with the meter movement resistance, Rm. This low resistance is called a shunt, RSH, and its function is to provide an alternate path for the total metered current I around the meter movement. Rm equals internal resistance of the meter movement, resistance of the basic DC ammeter circuit is as shown. In most circuits Ish is much greater than 1 meter, which flows in the movement itself. The resistance of the shunt is found by applying Ohm's law, where RSH equals resistance of the shunt. Rm equals internal resistance of the meter movement, resistance of the moving coil. Ish equals current through the shunt. 1 meter equals full-scale deflection current of the meter movement. I equals full-scale deflection current for the ammeter. The voltage drop across the meter movement is. The voltage drop across the shunt is equal to the voltage drop across the meter movement. The current through the shunt is equal to the total current minus the current through the meter movement. Knowing the voltage across, and the current through, the shunt allows us to determine the shunt resistance as. Calculate the value of the shunt resistance required to convert a 1 mA meter movement, with a 100 ohms internal resistance, into a 0 to 10 mA ammeter. The purpose of designing the shunt circuit is to allow us to measure a current I that is some number n times larger than 1 meter. The number n is called a multiplying factor and relates total current and meter current as. On a multiple range ammeter, the Ayrton shunt, or the universal shunt is frequently a more suitable design. One advantage of the Ayrton shunt is that it eliminates the possibility of the meter movement being in the circuit without any shunt resistance. Another advantage is that it may be used with a wide range of meter movements. The Ayrton shunt. The individual resistance values of the shunts are calculated by starting with the most sensitive range and working toward the least sensitive range. On this range the shunt resistance is equal to RSH and can be computed by. The voltage across each parallel branch should be equal and can be written as, in current and resistance terms we can write multiplying through by M. This can be rewritten as D'Arsonval meter movement used in a DC voltmeter. The basic Arsonvanol meter movement can be converted to a DC voltmeter by connecting a multiplier Rs in series with a meter movement. The purpose of the multiplier is to extend the voltage range of the meter and to limit current through the Arsonvanol meter movement to a maximum full-scale deflection current. To find the value of the multiplier resistor, first determine the sensitivity, S, of the meter movement. The sensitivity is found by taking the reciprocal of the full-scale deflection current. Voltage measurements are made by placing the voltmeter across the resistance of interest. This in effect places the total voltmeter resistance in parallel with the circuit resistance, therefore, it is desirable to make the voltmeter resistance much higher than the circuit resistance. Since different meter movements are used in various voltmeters and since the value of the multiplier is different for each range, total resistance is a difficult instrument rating to express. More meaningful information can be conveyed to the user via the sensitivity rating of the instrument. This rating, generally printed on the meter face, tells the resistance of the instrument for a 1 volt range. To determine the total resistance that a voltmeter presents to a circuit, multiply the sensitivity by the range.